Today we are going to talk about entropy in a similar way that we talked about enthalpy, meaning we're going to look at the entropy of chemical reactions. And entropy, that's the same definition as it was when we talked about thermodynamics several months ago. But we're going to apply that now to chemical reactions and see how it affects whether or not a chemical reaction can occur. So when we talk about entropy, we're going to do similar problems, and we're going to use a similar chart that we did for enthalpy. So we need to talk about, do reactions want to happen? That's where the entropy comes in. And then tomorrow, we're going to talk about combining enthalpy and entropy into one equation, and we will be able to predict whether or not a reaction will occur. So when a chemical reaction happens, what you are doing a couple different things. You're either combining two elements to make a compound, in which case those two elements are joining together in a chemical bond. Those chemical bonds store energy. Sometimes during a chemical reaction, you have a compound and you're going to break those chemical bonds and form, and your products end up being just the elements that were combined in the compound. Sometimes though, and in most chemical reactions, you're doing both. You're taking two compounds, a reaction happens that requires the breaking of chemical bonds and the remaking of chemical bonds in a different pattern to make new substances. Energies are going to be required and energy is going to be released in these processes. So a bit of a review. Energy is always required to break bonds. Always. It requires energy because it's stored energy within those bonds. That process is endothermic. The formation of bonds releases energy. So anytime you form a new substance, that's an exothermic process. And depending on the strength of the bonds, depends on how much energy is required to either break those bonds or form those bonds. So bringing enthalpy back into things for just a second. A reaction that breaks strong bonds and forms weaker bonds requires energy. So if you have a compound that has a really strong chemical bond, and then it goes on and forms a compound with weaker bonds, that's going to require energy. That's an endothermic process. If you have a reaction that breaks weaker bonds to form stronger bonds, that gives off energy. That's an exothermic reaction. And generally, when you're talking about thermodynamics, exothermic processes are favorable. Okay, they are more likely to happen under normal natural circumstances. So enthalpy involves energy. Okay. Entropy goes back to that second law of thermodynamics. So like how things tend to go to more disorder is the very simple way of thinking about entropy. Remember, like you go from order to disorder. That's just the natural state of things. But in reality, what's happening is it's a process. The natural processes tend to actually decrease the usable energy in the universe. And that's the second law of thermodynamics. And so entropy is a measure of that. Entropy is a measure of how much energy is dispersing throughout a system. Okay? The measure of the dispersal of energy in a system. A couple of things that regarding temperature. Entropy increases as temperature increases. So the amount of energy dispersal increases when you move the temperature, and that should make sense to you as you think about how molecules work. Increasing temperature, they get a little more fidgety and they start moving around more. So you're going to get more energy. Just like with the heats of formation, we use that table. We're going to use the same table. And if you noticed, you didn't need to notice it yet, but if you noticed on that big table on those 2 pages in your textbook that have all those compounds listed, and you look directly to the right to find the heats of formation or the enthalpies of formation, that next column over for all of those same compounds is going to be your entropies for these values. So entropies per mole have been calculated for many, many, many substances. So you don't have to do those calculations. We're just going to use them to figure out the entropies of reactions. And all substances have some entropy. So remember before, pure elemental substances did not have a value for enthalpy. They were 0. It didn't require any energy to make them. But for entropy, all of them will have a value. So you can't assume there are no zeros. Now we're going to use the same idea to calculate entropy changes as we did calculating enthalpy changes. We're going to take the difference in the sum of the products, those entropies, and then we're going to take the sum of the entropies of the reactants, and then we're going to subtract. It's going to be products minus reactants. And the same idea, the change in enthalpy, standard enthalpy, and these are standard conditions. So 25 degrees Celsius, 1 atmosphere, okay? Or 298 Kelvin in 1 atmosphere. So the sum of the entropies of the reactants subtracted by the sum of the entropies of the reactants. Did I say that wrong? Okay, let me say that one more time correctly. Not really sure how I phrased that. The sum of the entropies of the products, so you take them, you add them all up, and you use the coefficients in those balanced equations if you need to, minus, and you take the reactants, and you add all those up, multiplying by coefficients if you need to, you get that sum, and then you do the subtraction, products minus reactants. Okay, hopefully these calculations will be very, will flow easily for you because it's the same idea as the enthalpies of formation to find the change in the enthalpy problems. Okay, so all process increase the entropy of the universe. So something to keep in mind as you do this. All right. Does the reaction where we take ammonia, gas, and react it with hydrochloric acid as a gas, reacting those together to make ammonium chloride, does this increase or decrease the entropy? So I'm going to get out my textbook and I'm going to turn to those tables in the book on page 352 and 353. All right. And I'm going to find ammonium chloride. I'm going to walk you through this again, but it's on page 353. It's in the second column of compounds. And I see that ammonium chloride, I'm going to skip past the delta H, and I'm going to see that it is 94.6. And my units are going to be, now pay attention, this is important, and it's going to be really important tomorrow when we talk about something called Gibbs free energy. Okay. It's 94.6, and my units are joules, not kilojoules, joules per mole times Kelvin. Okay. So your units for these calculations are not just going to be kilojoules, they're going to be joules per Kelvin. That will be your final unit for these entropy calculations, joules per Kelvin, because we'll cancel out the moles based on the coefficients of your balanced equation. So here we go. So I looked up ammonium chloride, that's my product. I only have one product, so I really don't need to add anything. Okay, my entropy is 94.6 joules per mole times Kelvin. I have 1 mole understood to be there because of the coefficient being 1. So it's just 94.6 joules per Kelvin. That's the only product I have to worry about. But I do have 2 reactants. So I'm going to go to my table and I'm going to find ammonia. All right, ammonia is just above ammonium chloride, and that value is 192.8 joules per mole times Kelvin. I just looked it up in the table. Again, my balanced equation, there's a 1 understood, so there's my 1. My 1 mole cancels out my mole over here, and so I'm left with 192.8 joules per Kelvin. And then I'm going to do the same thing. I'm going to look up hydrochloric acid, HCl. That's over here on the first page, kind of towards the bottom, 186.9 joules per mole times Kelvin. All right, so I'm going to add 192.8 plus 186.9, and I get 379.7 for the reactants. And then I'm going to subtract. Now notice I've got a smaller number 94.6. And I'm going to subtract from that a bigger number, 379.7. So it's a smaller number minus a larger number. So my overall entropy is going to be a negative value. What that tells me is that the amount of entropy has decreased. Okay? And think about this. Look at what you got. You got a solid that's been formed, this is kind of cool, from two gases. So think about the lattice work. Think about how tightly those ions are packed in together to form ammonium chloride. They're tight. They're like, like that crystalline solid. Very organized. Very organized. That should make sense to you that the entropy, the disorder, for lack of a better term, or a simplistic way of looking at it, the disorder has decreased. You've gone from gases where molecules are flying all over the place to a solid, a much more organized form. So the chaos has decreased in that system. Kind of way to think about that, all right? That's what it means when you get a negative entropy. That means your product is more ordered than your reactants. And that should make sense simply from looking at the states of matter, okay? Those are the way all of these problems are going to go. Now, just to point out, and I want to go back to this one slide for just a second because I didn't focus on it as much as maybe I should have. All processes increase the entropy of the universe. What that means is that in general, our universe is going from order to disorder constantly. All the chemical reactions that are occurring, all the things that we do lead to more and more entropy. The other thing I want to point out is that when you look at this table, don't be surprised when you see, like if you go through and you look at these two pages in your textbook where you're going to be pulling these values from, the entropy, the S, the standard entropies of every substance are positive. It's always positive because every process, the creation of every substance has involved disorder. Okay, doesn't matter if it's element, doesn't matter if it's a compound, it's all required or caused an increase in entropy. Okay, so I'm going to, for your homework or your review work, you're going to do problems on page, just for today, on page 357. And you're not going to do them all because some of them we're going to cover Gibbs free energy tomorrow. But you're going to do some problems that involve entropy. They're going to be solved the same way, same time. This is a great example. Come back to it. Products, add them all up. Reactants, add them all up. Use your coefficients when you need to multiply. And then it's the same rule. Products minus reactants. Okay. Now, that's it for today. I'm going to check your assignment, post it with this video, and work on that. I hope to see you at office hours on Monday. And then tomorrow we will talk about combining the equation that combines entropy and enthalpy together, and we'll figure out which reactions will work and which reactions won't. All right. I'll see you guys later.